Hello, everybody. Welcome to Scalar's YouTube channel. This is Mahima Hans, and I'm a software engineer and a tech placement mentor. So, today we're going to be talking about sorting algorithms. And in this video, we'll be covering bubble sort and insertion sort. So, before we get on with the video, make sure to check out Scalar's free masterclasses by industry leading experts on Scalar's event page. So, let's get started with today's video. So let's talk about sorting algorithms. So sorting algorithm is essentially an algorithm which is used to sort the elements of a sequence in a particular order. So let's say we have an array of elements. We have 9, 3, 5, 1, 4. So these are randomly arranged. Now if I write them in this order, 1, 3, 4, 5, 9. Now they're sorted in ascending order. So this is essentially an example of sorting. We could also sort them in descending order like 9, 5, 4, 3, 1. Another example could be, say, sorting some of the alphabets in the order of their ASCII values. So say we have a couple of alphabets C, D, Z, A, B. They could be sorted like A, B, C, D, Z. So this is the essential idea of sorting, basically arranging elements in a specific order. So today we'll discuss some basic sorting algorithms and which will be bubble sort, selection sort and insertion sort. So if you're a beginner, I think this should be helpful for you and you'll be able to understand. So first let's talk about bubble sort. So bubble sort is the most basic sorting algorithm and it works by repeatedly swapping the adjacent elements whenever they're in the wrong order. Let's consider a simple array. We have 9, 8, 7, 5, 6. So let's try and run bubble sort on it to understand how it actually works. So we'll traverse from the left and we'll keep comparing the adjacent elements. And whenever the adjacent elements in the wrong order, we will try and move the larger element to the right side. So here we have 9 and 8. I'll swap them and move 9 to the right. It becomes this. Now we'll swap again because 9 and 7 are in the wrong order. So these will be swapped 8, 7, 9, 5, 6. We'll swap again and we'll have 8, 7, 5, 9, 6. Now we again check that 9 and 6 are in the wrong order. So we will swap them 8, 7, 5, 6, 9. So basically what we did is we were comparing the adjacent element. So first we compared the 0th and the first element, then the first and second, then the second and third, third and fourth, and finally, since there's no element after 9, we'll stop here. So if you notice, what we are doing is we are moving the larger element to the right every time. So at the end of our first iteration, what will happen is we'll have the largest element at the end of the sequence. So here you can observe that 9 comes at the end of the sequence. So the essential idea of bubble sort is that the larger element first gets to the right position that it has to be at. So this part gets sorted. Now we'll have to sort the remaining part, which is the first 4 elements. Okay, so let's see, we will start again. Similar manner, we'll be comparing adjacent elements and we'll be swapping them when they're not in the right order. So here we have 8, 7, 5, 6 and 9. Right. So now this part is sorted. We'll compare 8 and 7. 8 will move to the right. Now we'll compare 8 and 5. 8 will move to the right again. Now we'll compare 8 and 6. 8 will move further right. Now here we don't have to compare anymore because we already know that this part is sorted. This is already a larger element than any element before it. So this is sorted and now this part, like 8 is also at its right position. So now these two elements get sorted. We'll again continue. We'll again bring the next, which is the third largest element, to this position. And by now you might have understood that what is going to happen is that 7 is going to move to the third position. So now in the third iteration, the 7 will come to its correct position. So we'll start swapping adjacent elements and we'll definitely go till here because this part is already sorted. So we'll compare 7 with 5. it will be 5, 7, 6, 8, 9. Then we'll compare 7 with 6. It will be 5, 6, 7, 8, 9. So now these three elements are sorted, and our result of this iteration is 5, 6, 7, 8, 9. Now we have just two elements left. So we'll start once again. We'll compare the two adjacent elements 5 and 6. Now they're already in sorted order, so we don't need to swap them. So for this iteration, the result becomes the same 5, 6, 7, 8, 9. But you have to remember that since we have done another round of comparisons, we have found four largest elements for this array. So in first iteration, the largest element 9 got to its correct position. In the second iteration, 8 got to its correct position. In the third one, 7 got to its correct position. And in the fourth one, 6 got to its correct position. So we have this part sorted. Now we left with just one element, which is 5. Now for one element, we don't need to compare with any adjacent element, or we don't need to sort it out. So it's already sorted. So we can establish that for n elements, we have to do n minus 1 iterations, right? Because if we are sorting the n minus 1 elements out, if out of 5, we are arranging the 4 elements into their right positions, the last one will already get adjusted itself to its correct position. Like here, we sorted out 6, 7, 8, 9, and 5 already got to its correct position. So let's see what we've established, and let's try to write the pseudocode for our algorithm. So we established that we have to do adjacent element swapping for n minus 1 times. Also, when our array was 9, 8, 7, 5, 6, for the first time, we were comparing the first 4 elements with their adjacent elements. So for the first time, our loop was going from 0 to n minus 2. When we were doing second time, the 9 was already sorted. We had 8, 7, 5, 6 here. So we had to compare the first 3 elements with their next elements. So the next time, our loop went from 0 to n minus 3. The next time after that, this part was sorted. So we had 7, 5, 6, 8, 9. So we just had to take the first 2 elements and compare them with their adjacent elements. So it was 0 to n minus 4. So n minus 2 being 3 here, and 2 here, and 1 here. So since we have to do n minus 1 iterations, there'll be a for loop which will start from 1 and it will go till n minus 1. Now for each of the iteration, so for the first iteration, we noticed that we have to go till n minus 2, right? For the second, n minus 3. So for every iteration, we have to start from 0 and we have to go till n minus 1 minus I. So for the first one, we have to go till n minus 2. For the second one, when I equal to 2, j will go till n minus 3. So that way we'll have the code for this, and we'll be comparing element at the jth index and element at the j plus 1th index. If they're not in the right order, we'll swap them. So that's how bubble sort would work like. Let's get to the code to better understand it. Okay. So we have bubble sort here. We'll start from I equal to 1, I less than equal to n minus 1, I plus plus. Our j will always start from 0. We'll start comparing with from the first element. It will go till n minus 1 minus I, j plus plus. We'll be checking if array of j is greater than array of j plus 1. We'll be swapping them. Yeah, so let's run our code and check if it works. Let's just provide the input array as the one we were considering. 9, 8, 7, 5, 6. The length of the array is 5. Let's run the code. Yeah. So it sorts it out and our output is 5, 6, 7, 8, 9. So that's how bubble sort works. You can also write your own implementation of swap or use the inbuilt swap function which I'm using currently. So let's focus on the time complexity of this solution. So this loop will run n minus 1 times. So it will be rounding off to O of n. And this loop will also the max. So now let's focus on the time and space complexity of our code. So if you notice here, we were having n minus 1 iterations. So the length of the first iteration was from 0 to n minus 2. So it was n minus 1. We are going n minus 1 times on the first iteration, n minus 2 times in the second iteration, n minus 3, till the point it comes to 1. So it's essentially the sum of the first n minus 1 natural numbers. And for the sum of n minus 1 natural numbers, the formula would be n minus 1 into n minus 1 plus 1 upon 2, which boils down to n into n minus 1 upon 2. So we have it n square by 2 minus n by 2. And in terms of big O, our complexity would boil down to O of n square because we'll ignore the smaller term. So our time complexity for this solution is O of n square. And since we're not using any auxiliary space, so the space complexity for this solution would be O of 1. Now let's look at some of the disadvantages of bubble sort algorithm. So bubble sort algorithm has a time complexity of n square as we already discussed. So it would be very slow for large data sets. And it requires a comparison operator every time we are checking the relative order of the elements, and that can be inefficient in certain cases. There is also an advantage of bubble sort algorithm that it is a stable algorithm. So by stable, what I mean is, so we were having our elements as 9, 8, 7, 5, 6, right? So when we were making our first set of comparisons, when we were trying to put 9 at the right place, we were swapping it with 8, 7, 5, and 6. In this comparison, the relative order of the elements was maintained. 8, 7, 5, and 6, they were in the same order in our second iteration as well. And even when we were going to bring 8 at the last position, the relative order of 7, 5, and 6 were maintained. So whenever the relative order of elements in between the process of sorting is maintained, those algorithms are referred to as stable sorting algorithm, and bubble sort is one of them. So these are a couple of advantages and disadvantages of bubble sort. So let's consider a corner case of the algorithm. Let's say we have our array in already sorted order. So let's say our array is 1, 2, 3, 4, and 5. And let's run our bubble sort algorithm on this. We'll run the first iteration. We'll compare 1 and 2, they're already sorted. We'll compare 2 and 3, no need to swap. Then 3 and 4, they're also sorted, and 4 and 5. So here we see that in the first iteration, no swapping took place, which means our biggest element is already at the last position. And even if we continue further iterations, no swapping will take place because the array is already sorted. Even if we keep comparing the adjacent elements, it's going to be the same only. So in such cases where in any of the iterations we see that no swapping is taking place, that is because the elements have been sorted. So let's say we had 1, 2, 3, 5, and 4. We'll first compare these two, that's fine. These two are also fine. These two are also fine. And then we come at these and they will get swapped. Now when we go over this again, we'll find that we'll not be able to do any further swapping. So this means an array is already sorted. So this establishes a fact that whenever no swapping is taking place on comparing two adjacent elements, that means that the array is already sorted and we can stop our iterations there. So that's basically optimizing our code a little bit to reduce the time complexity. So code wise, let's just say we have a variable bool swapped, and let's just keep it as false initially. So whenever any swap is happening, whenever any order is messed up and we are swapping it, we'll just set our swapped variable as true. Now we'll check after our iteration, after all the comparisons are made, we'll just check if swapped is false. So if no swapping was done, we can break our loop here only. So this means we don't need to do any further iterations, right? Like when in the first iteration we found out that no swapping was occurring, we can stop here only. So that's how this works. So for this particular case, what we can say is we only took one iteration, right? Because the outer loop only ran one time. So for this particular case, our time complexity is O of 1 here and O of 1 on the O of n on the second loop. So the time complexity boils down to O of n in this case. So this is the best case complexity of bubble sort. The average and worst case complexities are still n square, but this is a corner case which gets solved in O of n. Let's quickly check the number of iterations that we are going through in different examples. So first we have 9, 8, 5, 7, 6. I'll simply maintain a count variable to count our iterations. And in every iteration, we will just do a count plus plus. And as and when we encounter that no swapping was done, we'll break and the count of iterations will stop. So for this example, let's print our number of iterations. So number of iterations in this example is 4. If we go over our example 1, 2, 3, 4, 5, which is an already sorted order. Yeah, you'll see that number of iterations is 1. So that's why your complexity reduces here. This is a small optimization you can do in your bubble sort algorithm. Now let's move on to the insertion sort algorithm. So insertion sort is a simple sorting algorithm that works similar to the way you sort playing cards in your hands. So our array will be virtually split into a sorted and unsorted part. Let's just take an example and I'll explain through that. So let's say we have this array 4, 3, 2, 10, 1, 5, 12, 6. Initially, one element we know is always sorted. Let's consider this part is sorted. What we'll do is, we'll pick one element from the unsorted portion and we'll insert it at the right place in the sorted portion. So first we'll pick 3. That's the first element in the unsorted portion. Now we start from here. We start looking at the sorted portion from the end. It's sorted. We can traverse at it from the end. It will be a descending order. So we pick up 3. It's smaller than 4. We go to this position and we insert it. So 3 gets inserted here. Our array looks like 3, 4, sorted, 2, 10, 1, 5, 12, and 6. Now we pick the next element, which is 2. We start from the last element of the sorted part. We check 2 is smaller than this, 2 is smaller than this, so 2 will come here. So our array becomes this. This is our sorted part. We have 10, 1, 5, 12, and 6. Now we pick 10 and we check the last element of the sorted array. It's bigger than that. It gets inserted here only. So now 10 gets the place here. In the sorted part, we have 1, 5, 12, and 6. So now we pick 1 and we start with the sorted part of the array. We compare 1 with all the elements starting from 10. Smaller than 10, smaller than 4, smaller than 3, smaller than 2. We find out that the correct position for 1 is the 0th position. So we place 1 here and then we just see that the unsorted part now is 5, 12, and 6. So now we move on to 5. We start to find the right place for 5. We start with 10. And 5 is larger than 4, so we stop at 10 itself. And the correct place for 5 is now after 4. and this is our unsorted part. So now we realize that whenever we are trying to find the right place for any element in the unsorted part, we start from the sorted part and we traverse till the place where the elements are bigger than that element. So say we were finding the right place for 5, we were starting from the end of the sorted part and we were stopping as and when we find an element which is smaller than 5, because we have to insert 5 at that particular position. So that's how we determine till where we have to run our loop. So when I say we are picking up the elements from the unsorted part and we are inserting it at the correct position in the sorted part, how this will work in our code, let's try to understand that. So when we're picking up 3 and we're trying to insert it here, so what we're doing is we are taking all the elements which are greater than 3 and we're shifting them by one place. So let's say we'll store 3 in some variable, okay? Let's just keep a variable key and we are storing 3 here. So we start from the end of the sorted part, which is always one index less than our current element. Because whenever we are picking an element, the elements before that are already sorted. So we take the key as 3, we start from the sorted path's end, and whenever an element is greater than the key, we move it one step ahead. So we move 4 here and we insert 3 here. Now let's move to the next element. We pick up 2. Our key becomes 2. We move 4 here, we move 3 here. Both of them were greater than 2. So we move both of them one step ahead. And we find the right place for 2, which is the first index. So this is how our array looks like. Similarly, when we pick up 10, we try to iterate from the end of the sorted part, but we find that the first element we get is smaller than 10, so we don't have to move anything one place to the right. Now we have our sorted part as 2, 3, 4, 10, and we reach 1. So now 10 is greater than 1, move it one step to the right, move 4 one step to the right, 3 and 2 also, and insert 1 here. So we got 1, 2, 3, 4, 10, and the next element is 5. So when we reach at 5, we start from 10 again. We see that 10 is greater than 5, so we move 10 one place ahead. And 4 is smaller than 5, so we stop here. So now and this 5, which was already stored in our key variable, will be placed here. So our array becomes 1, 2, 3, 4, 5, 10. This is the sorted part. So now let's move to the pseudo code of our algorithm. So initially we considered that our first element is already sorted, right? So what we have to do is take each one of these n-1 elements and put them at the right place in the sorted part. So we will be definitely having n-1 iterations here. And we will be sorting out, which means we'll be inserting elements from index 1 to element from index till index n-1 at the right position in the sorted order. So let's just keep our outer loop to start from 1. Let it go till n-1 and it will be I++. Now for each element what we're doing, we're considering that element as the key. So we'll just say our key is ARR of I, and then we will just start from one element before that. So as I already told, whenever we are picking any element, all the elements before that will be already sorted. So we will start our inner loop from I-1. We will go till j is greater than equal to 0. And the other condition that I told you about is we only have to traverse in the reverse order till the time we get to an element which is smaller than or equal to the current element that we are looking at. So we'll only move the elements which are greater than the current element to the right position. So our while loop condition would be till the current element in the iteration is greater than our key element, we have to move it one place forward. So we will just write ARR of j plus 1 equal to ARR of j. And we'll just keep moving in the reverse direction. After that, we also have to place our key at the right place. So whenever our moving forward to the right element stops, so say we were starting from here, Let's say we are at 2. This is sorted. J is 1 here. We moved this to second place. We moved this to first place. Now this is the place where 2 has to come. So we have to make sure that after this while loop, we have to insert our key element to the right position. Let's write code for it and it will get better. So let's write our function insertion sort. We'll take an array, take the number of elements. Let's cut this gap. So as per the pseudocode, we will start with the first element. We have to do n minus 1 iterations to put each of the n minus 1 elements in their right place. So I'll start with I equal to 1. I'll go till n minus 1, I plus plus. We'll consider a key. The key will be the current element, the element at index I. Now to start putting the elements to the right, we have to start with j equal to I minus 1, just the previous element. And it will never go out of bounds because we're always starting I with 1. So that works. Now let's write our loop to move the elements which are greater than the current element just one step to the right. So we will go while j is greater than equal to 0. And our current element in the iteration is greater than the key. In that case, we just have to move it one step ahead. Equal to rearrange. And we just have to decrease j by 1 to traverse in the reverse order. Now we will populate arrj plus 1 with our key element. Why j plus 1? Because when we transferred 3 to the right, so we were doing it for 2. Here j was 1. So when we transferred 3 to the right and then we moved to j equal to 0, we transferred 4 to the right, then we moved to j equal to minus 1 and our loop exited. Now we have to place 2 at one position greater than this j. So we have to place our key element at j plus 1. So that's why we are doing array of j plus 1 equal to key. Now let's run this code and see if it works fine. I'll just write insertion sort here. I will also change our array to the one we were looking at in our example. Let it be 4, 3, 2, 10, 1, 5, 12, 6. And our n will be 8. Let's run the code. Let's see what error we have. Insertion sort, there's a quick syntax error, spelling error. Yeah, so we got our elements in the sorted order. So this is how insertion sort works. Now let's work on the complexity of insertion sort. So we are having an outer loop which is going for n minus 1 iterations. So averaging out its O of n. And for this loop also, so let's now analyze the time and space complexity of our quicksort solution. So initially we considered this part as sorted, right? Whenever we are picking up any element, in the worst case, we will go through all elements before this element. So when we are picking element at index 1, we will go through one element at max. We're picking up this element, we will go through these two elements at max. Maybe we find a pause in between and we have to stop putting the elements towards the right. But I am currently considering the worst case, that how many elements at max I have to traverse for every element. Now, when we are at index 3, the maximum number of elements I have to go to is these 3. So this looks like our number of elements to traverse will be increasing by 1 every time. So it will be like this. So it will be like the sum of first n minus 1 natural numbers, which is n minus 1 into n minus 1 plus 1 upon 2. So n into n minus 1 upon 2. And this again boils down to O of n square. So O of n square is the worst case time complexity. And in average case also, the inner loop will run at max n times. Like we can take the upper limit to n. And so in the average and the worst case, the time complexity is O of n square. Now let's talk about the best case complexity. So the best case scenario for our insertion sort algorithm is when all the elements are already sorted. Let's consider that case. Let's say I have 1, 2, 3, 4, 5. We consider this part as sorted. We pick up 2. We start with this, our first element. Now in our code, we are running our while loop on a condition that our current element in our traversal of the sorted array is greater than the key. But here it is not greater. So we'll not go through this while loop. Similarly, for the third element, this part is sorted. For the element 3, basically, the element with key equal to 3. Here also, when we start our while loop, this condition will be false, so it will not run in that case. Again, for the next element, it will the while loop will not run. So basically, the time complexity for this loop becomes O of 1. We just have to go through all of these elements, and while loop will not run in any of the cases. So our time complexity will become O of n into O of 1, which is O of n. So that's the best case time complexity of insertion sort algorithm. So insertion sort is also a stable sorting algorithm because it preserves the relative order of the elements in the output array. So that's it for today, guys. Hope it was helpful. If you have any doubts, make sure to mention them in the comments section and we'll be happy to help. Make sure to like and share this video and subscribe to Scalar's YouTube channel for more such insightful content. Thank you and see you.